Friends, last lecture we already discussed some acids and we determine the relative strength of these acids using the various structural effects. Today we are going to discuss some acids and using the structural effects we determine the relative strength of acid. So first we take a example, the benzoic acid and cyclohexane carboxylic acid. So we take an example of benzoic acid and we take the second acid and cyclohexane carboxylic acid. And we remember in this case, this benzoic acid is a stronger acid than the cyclohexane carboxylic acid. So what is the reason? Because we remember in case of benzoic acid, the acid group or COOH group is attached to the sp2 carbon, and this sp2 carbon gives the minus I effect. When we think about cyclohexane carboxylic acid, this acid group is attached to the sp3 carbon and sp3 carbon gives the plus I effect. And we already discussed so many times, when there is a minus I effect is there, then conjugated base is stabilized and then acid is more stronger. So in case of benzoic acid, there is a minus I effect because acid group is attached to the sp2 carbon and it gives the minus I effect. So that's why in case of benzoic acid, the conjugated base is stabilized, and that's why the benzoic acid is a more stronger acid. But in case of cyclohexane carboxylic acid, acid group is attached to the sp3 carbon, it exerts the plus I effect, and when there is a plus I effect is there, then conjugated base is destabilized, and that's why the cyclohexane carboxylic acid is weaker than the benzoic acid. Then we take a next example and we take a 4 compounds, and out of that 4 compounds we arrange according to the increasing order of acidity. So first is a benzoic acid. We attach the methyl group at a ortho position, so orthomethyl benzoic acid. Then this is a metamethyl benzoic acid, and you take last example, this methyl group is at para position. And when we want to compare the acidity of these 4 acids, we remember this methyl group donates the electron. We know because methyl group is an electron donating group, and when there is a methyl group is there, then it gives the electron donating inductive effect. So in benzoic acid there is no methyl group, so the benzoic acid is a more stronger acid out of these 4. Then we want to compare the acidity between these 3 isomers. This is the orthomethyl, this is a metamethyl benzoic acid, this is a paramethyl benzoic acid. And when we compare the acidity between these 3, then we remember what happened. The distance between acid group and methyl is small here, it is less, and so ultimately here is a more plus I effect. So plus I effect is a more as compared to the this is a para isomer and the meta isomer. But when we remember in this case, there is a methyl group at a meta position, then this methyl group gives less plus I effect as compared to the ortho and the para isomer. So that's why which is the first more acidic? Benzoic acid. Then this is the first one. Then we remember after benzoic acid there is the acidity of metamethyl benzoic acid is more, because this methyl when at a meta position it gives a less plus I effect, and so ultimately the meta is more stronger than ortho and the para. Then we compare the ortho isomer and the para isomer. When we remember there is a distance between acyl group and methyl is more again, and so that's why in this case we remember in para isomer the plus I effect is less, so that's why which is this third or para isomer is more acidic as compared to the ortho, and we remember ortho is or orthomethyl benzoic acid is the least acidic. So that's why in this way we compare the acidity of various compounds, because the methyl it gives the plus I effect, but we remember when the methyl group at a meta position then it gives the less plus I effect, and that's why this meta isomer is more acidic as compared to the ortho and the para, and the ortho isomer is the least acidic because it gives when the methyl group at a ortho position it gives the more plus I effect, and so that's why the orthomethyl benzoic acid is the least acidic and benzoic acid is more acidic. When we explain such a type of examples, then we take a next example and we compare the acidity between orthohydroxy benzoic acid. This is the orthohydroxy benzoic acid and parahydroxy benzoic acid. So why the orthohydroxy benzoic acid is more stronger acid than the meta and the para isomer or parahydroxy benzoic acid? Because we remember after dissociation of this acid there is a formation of conjugated base. Then after dissociation of this parahydroxy benzoic acid there is a formation of this is a conjugated base is there, but in which case the conjugated base is more stabilized or stabilized, because we remember in a first case, in case of orthohydroxy benzoic acid, the conjugated base is well stabilized by hydrogen bonding, or it is called intramolecular hydrogen bonding. Because we remember what happened in orthohydroxy benzoic acid after dissociation, formation of conjugated base, and this conjugated base is well stabilized by intramolecular hydrogen bonding between the hydrogen of OH and O- of this acid group, and it makes the orthohydroxy benzoic acid is a stronger acid than the para as well as the meta isomer. But what happened in case of the parahydroxy benzoic acid, the conjugated base is not stabilized by hydrogen bonding, because the distance between this is a acid group and the OH is large, so that's why there is hydrogen bonding is never possible. So that's why the orthohydroxy benzoic acid is more stronger than the para and the meta isomer. Then you take a next example and we compare the acidity of these four compounds. You take or three compounds. You take this first example, then you write the second one, We take a third example. And we want to compare the acidity. So what happened here? In this case, there is a two acid group is there. COO, this is one COO, this is second COO. So what happened here? When the distance between these two acid group is small or less, distance is less, so ultimately there is a minus I effect is more. In case of the distance is very less, in this case the distance between these two acid group is increases. Again here the distance between these two acid group is also increases. So ultimately in this case the minus I effect is more because the distance between these two COOH group is less. In this case the distance is increases, the minus I effect is decreases. Again here the distance between these two acid group is increases, then the minus I effect is decreases. So ultimately which is the more stronger? This is a more stronger acid, then this, and then the last one. Because the distance between these two acid group is increases, then minus I effect is decreases, and when there is less minus I effect, then your acid is a weaker one. Then you take a next example, and we compare these two acids, the malic acid and the fumaric acid. This is the malic acid, this is the fumaric acid, and we want to compare the acidity between these two acids. So what happened? When we dissociate both the acids, and we call this is the first dissociation. In this case the first dissociation. And what happened in case of the first dissociation? We get the conjugated base. We dissociate this fumaric acid and we get here conjugated base. What happened in first dissociation? In case of malic acid, in first dissociation, the malic acid is a stronger acid than the fumaric acid. Why? Because what happened? After first dissociation, in case of malic acid, the conjugated base is well stabilized by intramolecular hydrogen bonding. Suppose this one. This is hydrogen bonding. So conjugated base is well stabilized by intramolecular hydrogen bonding in case of malic acid. So that's why the malic acid in first dissociation, it is a stronger acid than the fumaric acid. But what happened in case of the fumaric acid? Two acid groups, they are apart from each other, they are trans to each other, and so ultimately what happened? After first dissociation, the conjugated base in a fumaric acid is not stabilized such type of hydrogen bonding which is present in a conjugated base of malic acid. So that's why in first dissociation, fumaric acid is a weaker acid as compared to the malic acid. But what happened in the second dissociation? We do the second dissociation. We do the another second dissociation of the fumaric acid. What happened in the second dissociation? And when after second dissociations, we get this is the dianion species. In case of fumaric acid, we also get this is the dianion species. So what happened? What happened in a second dissociation? In second dissociation, we remember the pumeric acid is a more stronger acid than the malic acid. So why? So reason is that what happened in case of the second dissociation? In case of malic acid, we want to dissociate the second hydrogen from acid group, then we want to remove the hydrogen bonding. And we want to remove the hydrogen bonding, it requires more energy. So the dissociation is decreases. And second reason is there, after dissociation or second dissociation, there is a formation of dianion species. The like charges, they are come closer, and that's why there is a steric repulsion. So that's why here is a steric repulsion between these two dianion species. And due to the steric repulsion, what happened? This conjugated base is destabilized in the second dissociation in case of malic acid. But what happened in case of the pumeric acid? When the second dissociation takes place, then such a type of steric repulsion is not possible here, because these dianion species is formed, but both the anions, they are apart from each other, they are trans to each other, and so there is no steric repulsion. And due to there is no steric repulsion, the second dissociation of pumeric acid is easy, and that's why in second dissociation the pumeric acid is a more stronger acid than the malic acid. So in this way, we remember in first dissociation the malic acid is stronger, but in second dissociation the malic acid is a weaker acid. In case of pumeric acid, in first dissociation it is a weaker acid, but in second dissociation it is a stronger acid. So in this way, we compare the relative acidity of various acids using the various structural effects. Then we want to know the what type of effect there are effects on the base strength. So that's why in case of acids, we take various examples of acids and we determine the relative strength of acid using the various structural effect, like inductive effect, resonance, then hydrogen bonding. Such a type of effects or structural effects, they affects on the strength of acid. Then we think about the organic bases. Because we already discussed the various examples of acid, so we think about the organic bases. So what is meant by the base? Base is nothing but the compounds which having the lone pair of electron, and this lone pair of electron, they are given to the H plus, and there is a formation of BH minus or BH plus. So base is nothing but lone pair of electron donor, and then the strength of base is depends on the following factors. Factors affect the strength of base or bases. So which factors they are affects? So first important factor, the availability of lone pair of electrons. Means what? So this is the first criteria for the base, the availability of lone pair of electron. Because when the lone pair of electron is available and this lone pair of electron is easily available for donation, then the base strength is increases. So the first important point is there, the base having the lone pair and it is easily available for donation, then the base strength is increases. Then next one, the electronegativity of B. The electronegativity of base B. What happened? When the base having the more electronegative, then it having the less tendency to donate the lone pair of electron, and when it having the less tendency to donate the lone pair of electron, then ultimately the base strength is decreases. So this is the second factor is also important, the electronegativity of base. When the base having the more electronegative, it having the less tendency to donate the lone pair of electron to H plus or other species, ultimately the basicity is decreases. Then the structural effect in B, the next point, structural effects in base B. Structural effect means what? Suppose the groups which are attached to the base or B, which gives the minus I and minus R effect, means electron withdrawing inductive effect and electron withdrawing resonance effect, then the base strength is decreases. Because when the groups they are attached to the base which withdraw the electron from the base, then electron density around the base is decreased and ultimately the base strength is decreased. So the groups which gives the minus I and minus R effect and they are attached to the base B, then the base strength is decreases. Then when the groups they which are attached to the base and it gives the plus I and plus R effect, then base strength is increased. And why the base strength is increased? Because what happened, the groups they are attached to the base, they donate the electron to the base, and when they donate the electron to the base, then ultimately what happened, electron density around the base is increased and base is easily donate the lone pair of electron to the H plus, and so that's why the base strength is increases. So this is the third factor, the structural effect in B. When there is a minus I and minus R effect, then the base strength is decreased, and when there is a plus I and plus R effect is there, then the base strength is increased. And then last point is there, and this last second last point is there, the stability of conjugated base, the fourth one, stability of conjugated acid, not a base. What happened? After base is donate the lone pair of electron, there is formation of a conjugated acid, and when the conjugated acid is more and more stable, then the base strength is again increases. So that's why the stability of conjugated base is more, acid is more, then the base having the more strength. And last part, an important point or point, the nature of solvent. I write here the fifth one, the nature of solvent. Nature of solvent. So nature of solvent is also affects on the strength of the base. And when we take one simple example, suppose RO minus, this is your base, donate the lone pair of electron to H plus, and there is a formation of ROH. So we remember what happened when the nature of base or nature of solvent. So solvent having the two types, there is a polar solvent, there is a non-polar solvent. What happened? When conjugated acid is a charged species, when the conjugated acid, when base donate the lone pair of electron and there is formation of a conjugated acid, and conjugated acid is a charged species, then polar solvent increase the strength of base by stabilizing the conjugated acid through the solvation. Means the conjugated acid is a charged species, then polar solvent increases the basicity. Because polar solvent is stabilize the charged species conjugated acid through solvation. But when such a type of base is a charged species, suppose RO minus, it is act as a base, but base having the charge species, then polar solvent decreases the base strength, because base itself solvated by the polar solvent and the basicity is decreases. But when the base having the charge species, then non-polar solvent increase the base strength, because in non-polar solvent the solvation of charge species base is never takes place, and so that's why when the base having the charge species, the non-polar solvent is increase the base strength and polar solvent decrease the base strength, because base itself solvated by the polar solvent. So that's why we remember when the conjugated base is a conjugated acid is a charged species, then polar solvent increase the basicity by solvation of conjugated acid. And when the base itself is a charged species, the non-polar solvent increases the base strength and the polar solvent decreases the base when the base having the charged species. So this is the 5 factors. They are effects on the base strength. Availability of lone pair of electrons, that is a must. Electronegativity of base increases, then tendency to donate the lone pair of electrons is less, base strength is decreased. The structural effects in a B or base, when there is a minus I and minus R, the base strength is decreases. When there is a plus I and plus R, base strength is increases. And then last part, the nature of a solvent. So we already discussed, when polar solvent is there, then your conjugated acid is charged species, then base strength is increased. When non-polar solvent is there, then your base is the charged species, then in non-polar the base strength is increases. So in this way we discuss these 5 factors, they are effect on a base strength. Then we take one example. And we compare the relative basicity of aliphatic bases. So here we take ammonia, methylamine, dimethylamine, and you take a trimethylamine. So what happened here? We want to compare the basicity of these 4 bases. So this is the NH3. Then we take example of methylamine. There is one methyl group is there, it gives the plus I effect. In dimethylamine, there is 2 such methyl group, it gives a 2 plus I effect. And in this case, such a type of 3 methyl group is there, it gives the 3 plus I effect. When we compare the plus I effect, here there is no plus I effect. We remember here the 1 plus I effect. Here is a 2 plus I effect due to 2 methyl group. And here we compare, there is a 3 plus I effect due to the 3 electron donating methyl groups. When we discuss only or when only see the plus I effect, then the tertiary amine or trimethylamine is more stronger base when only we consider the plus I effect. But in actual, tertiary amine is not stronger base out of these 4, but the secondary amine is more stronger base out of these 4, and the new effect is there, that is called the solvation. Means when we think about only the plus I effect, then tertiary trimethylamine having the more plus I effect, so it is more basic when we think about the plus I effect, but actually it is a weaker one as compared to the secondary amine, and secondary amine is more stronger base than the tertiary amine, and that's why that there is one effect is there, and this is called the solvation.